Operational and implementation aspects, purpose and coverage. The operational and implementation aspects of a complex control loop describe how the loop behaves under all process conditions, how it is configured in the control system, and how operators interact with it. This section is essential for translating design intent into actual system behavior and ensuring that all modes of operation, normal, abnormal, and transitional, are explicitly defined and tested. It also guides system integrators in configuration and helps operators understand expected responses under varying scenarios. Scope of operational modes. The following modes and conditions are addressed for each complex control loop. Startup details the initialization procedure, including how controllers and valves are brought online, bumpless transfer requirements, default states, and any special logic for temporary bypass or override during ramp-up. Normal steady-state operation describes the loop's expected behavior under design operating conditions. It includes control logic, set point tracking, interaction with cascaded or feed-forward elements, and typical tuning behavior. Crippled mode operation defines fallback logic and degraded operation scenarios when one or more loop inputs, e.g. analyzers, feedback signals, control valves, are unavailable or unreliable. This might include switching from cascade to manual, holding last good values, or reverting to simpler control strategies to maintain plant stability. Shutdown and abnormal conditions specifies the loop's actions during planned shutdowns or emergency events. Includes fail-safe positions, interlock responses, output limits, and any automated reset behavior. Also highlights alarms or protective overrides relevant to shutdown states. Calculation requirements and data integrity. Any calculations used in the control logic must be fully described. This includes formulae and logic blocks, units and accuracy expectations, calculation limits and validation logic, e.g. clamp values, deadbands, sequence or order of operations where multiple calculations are chained. All constants used in calculations must be documented with the following: value in units, method of derivation, e.g. from vendor curves, simulation output, source reference, e.g. datasheet, design basis document, document identification, title, revision, and section. This ensures engineering traceability and supports revalidation during retuning, upgrades, or audits. Implementation considerations. This subsection outlines the specific control system configuration requirements, including controller modes and default settings, algorithm selections, e.g. PID type, anti-reset wind-up logic, tracking requirements for initialization, cascade transitions, or manual override, output limitations and ramp rates, use of signal conditioning, e.g. filtering, deadband application, special logic elements such as selectors, overrides, or interlocks. Any deviation from standard implementation practices must be justified and described in detail. Operator interface and interaction details how the operator views and interacts with the loop, including faceplate design expectations, e.g. visible parameters, control buttons, parameter visibility, e.g. set point, output, mode, alarm and timer settings relevant to operator actions, requirements for manual operation, override switches or diagnostic displays, restrictions or permissions for operator intervention during different phases. The goal is to ensure the loop is understandable, operable, and safe from the field control room or HMI interface. Interfaces and dependencies describes how the control loop interacts with other systems, such as other control loops, cross-loop interactions, or shared set points, Instrumented Protective Functions IPFs, optimizers or APC platforms, supervisory systems, e.g. ODS, historian, mimic panels, vendor packages, or multi-subsystem architectures. Clear interface definitions are necessary for integration testing, fault diagnosis, and seamless automation across unit boundaries. Timer settings and alarm handling. For any timers within the control logic, define the reason for the timer and its role in the logic. State whether the timer should be adjustable by operators. Provide the basis for the default value and allowable range. Alarm set points and trip levels are not documented in the narrative, but must be referenced to the appropriate database, e.g. INTools, where they are maintained with revision control and accessible for extraction into setting lists. Summary. This section ensures that the control logic is not just theoretically valid, but practically operable, maintainable, and fully integrated into the broader plant automation system. It supports robust configuration, commissioning, and lifecycle operation by aligning design logic with actual system behavior, control system capabilities, and operator expectations. Detailed narratives for logic, sequence, and batch systems. Purpose and application. Logic, sequence, and batch systems govern the safe and repeatable execution of complex operational tasks such as equipment startup, batch processing, interlocking, or shutdown procedures. These tasks often involve multiple steps, conditions, confirmations, and system interactions that cannot be fully represented on PEFs or simplified logic diagrams. Detailed narratives ensure the control intent is fully documented, unambiguous, and implementable in the control system. This section is essential for systems where order, timing, and interdependencies directly impact safety, product quality, or equipment protection. It provides a step-by-step breakdown of control logic that must be understood by DCS PLC programmers, commissioning teams, and operations personnel. Structure and core components. Each logic, sequence, or batch control narrative includes the following key sections. Objective defines the process purpose of the logic or sequence, e.g., to automate reactor charging, ensure safe compressor startup, or perform vessel depressurization. It explains what the sequence achieves and why its automation is necessary. Functional description provides an overview of how the sequence or logic is structured and functions. It describes the operating context, manual, semi-automatic, or fully automatic, sequence initiation and termination conditions, system components involved, valves, pumps, interlocks, the normal progression of steps and logic branches, use of overrides, ignores, or fallback paths. If the system operates in multiple modes, e.g. batch, continuous, cleaning, each mode is outlined with its flow logic. Step logic and programming approach. All sequences are broken into discrete steps using a modular approach. Each step performs a defined process action, e.g. open valve, start pump. Awaits a condition or confirmation before progressing, may include logic to handle abnormal or off-spec situations. Logic is described using structured English pseudocode to ensure clarity and alignment with control system programming. This includes commands like open, close, if, then, wait, goto, and reset, accompanied by tag numbers and service descriptions. Sequence function charts, SFCs, are used to represent the flow of logic graphically, showing states, transitions, and conditions between steps. For complex sequences, detailed SFCs may be nested under parent steps. A tag list with service descriptions is provided to accompany the pseudocode for reference and validation. Operational and implementation aspects. This section covers how the sequence behaves under different process conditions. Normal sequence describes how the system executes under expected operating conditions, including preconditions for each phase. Abnormal sequence defines how the system responds to failures, invalid conditions, or unexpected feedback. These paths lead the process to a safe state and prompt operator intervention. Interlocks lists hard or soft interlocks that must be met before specific steps are allowed to execute. These include dependencies between valves, drives, feedbacks, or process states. Ignores describes scenarios where the operator can temporarily override a failed feedback signal, e.g., valve position, to continue processing under controlled risk. Ignores must be manually reset at the end of the sequence and are typically logged for audit. Initial conditions details all prerequisites for starting the sequence, e.g., all valves closed, vessel empty, feedbacks reset. Operator actions specifies required operator interactions such as manual confirmations, recipe selections, or override activations. These actions are often tied to push buttons, selector switches, or control system inputs. Calculations identifies any logic-based or value-based calculations required during the sequence, such as dosing volumes, ramp durations, or conditional timers. Interfaces highlights interactions with other systems, such as safeguarding blocks, recipe management tools, or inter-unit signals. Restart logic explains how sequences are resumed after an abnormal stop, including validation checks and reentry points. Configuration particularities notes any special programming methods, code reuse practices, or platform-specific considerations. Sequence timing and visualization. For multi-valve or motor-driven systems, valve equipment timing charts are used to show the state of each component during each step of the sequence. This provides clarity on overlaps, delays, or critical transitions and is essential for testing and commissioning. History and version tracking. Each logic narrative includes a history section to track changes in sequence logic, justification for overrides or resets, and outcomes of previous design revisions. This prevents reintroduction of failed logic and provides an audit trail for future modifications. Deliverables and execution. The full sequence logic must be ready in a structured format for implementation by the control system vendor. Extensive code commenting is expected during the final programming stage to aid in debugging and long-term support. The final narrative serves as a working reference during FAT SAT, SSAT, and must remain aligned with programmed code and operator graphics. By providing a clear, stepwise, and operator-aware description, this section ensures logic and batch processes are implemented safely, consistently, and with full process visibility. Instrumented Protective Function IPF narratives. Purpose and role in process safety. Instrumented Protective Function IPF narratives document the logic, functionality, and operational intent of automated safety functions designed to prevent hazardous events. IPFs are used to detect abnormal or dangerous process conditions and bring the system to a defined safe state using dedicated instrumentation and final elements, e.g., isolation valves, shutdown signals. These narratives are developed for all IPFs in a process unit, including those embedded within safeguarding logic, UZ blocks, as well as standalone protections. They ensure that each protective function is clearly identified, justified, and understood across engineering, operations, and safety disciplines. The IPF narrative forms the foundation for safety integrity level assessments and supports configuration of the Instrumented Protection System, IPS. Scope and structure. Each IPF narrative includes an overview of the protective strategy across the unit, a detailed breakdown of each IPF, including its objective, logic, inputs, outputs, and response time requirements, sequences and special logic where standard trip conditions do not apply, alarm narratives for operator notification, where applicable, diagrams and logic representations, e.g., cause and effect diagrams, functional logic diagrams. IPFs may be implemented within UZ blocks, logical groupings of interrelated protections, but each individual protective function must be documented and evaluated on its own merits to capture the specific hazard it addresses. Content elements of a detailed IPF narrative. Each IPF is documented with the following components. Objective. Defines the specific hazard that the IPF is designed to prevent, e.g., vessel overpressure, backflow contamination, compressor surge. It includes the consequence of not acting, impact to personnel, environment, equipment, or production, and explains the safety design intent. Functional description describes how the IPF works, what initiates it once are taken, and how the system ensures that the hazard is successfully mitigated. It includes initiating elements, e.g. pressure transmitters, level switches, temperature sensors, trip logic, e.g. 102 voting, sequential triggers, final elements, e.g. valve closures, equipment trips, success criteria, what constitutes a successful protection response, any secondary or supporting actions, e.g. interlocks to isolate auxiliary systems, operational and implementation aspects, details the IPF behavior in all operating modes, startup, normal, shutdown, and abnormal. This includes mode-specific applicability of the IPF, reset, override, and bypass logic, maintenance and test handling, e.g. use of maintenance override switches, alarm and enunciation behavior, process safety time and response time requirements, specific system configuration requirements, e.g. SIL rated to devices, diagnostics, logic and sequence representation for IPFs involving multi-step logic or coordination across systems, e.g. furnace purge sequences, safe startup interlocks, detailed logic diagrams are included. These may consist of functional logic diagrams, FLDs, sequence function charts, SFCs, pseudocode structured logic, cause and effect diagrams, CEDs. While not embedded in the IPF narrative, cause and effect diagrams are developed in parallel and referenced within the document. CEDs show the relationship between initiators and final elements for each UZ block. IPFs are marked within these diagrams for clarity, and any shared trip logic is shown in context. These diagrams are essential for understanding interdependencies between multiple IPFs and for facilitating system configuration and testing. Alarm narratives. Where alarms form part of the IPF strategy, e.g., operator intervention-based functions, alarmed-only protection layers, a narrative is included for each alarm. This includes the purpose of the alarm, the likely cause of activation, consequences of no operator action, the expected operator response, whether the alarm is an IPF, operational message, or pre-alarm. Each alarm is evaluated individually to ensure proper prioritization and classification. Implementation and lifecycle considerations. IPF narratives are developed during the definition phase based on anticipated CL levels and updated post-classification to reflect formal SIL assignments and implementation decisions. They must be finalized before plant startup and maintained as part of the facility's safety documentation. While IPF requirement sheets or safety lifecycle management software may supersede parts of the narrative, core descriptions, especially for sequences and logic flow, remain relevant and irreplaceable. These narratives provide transparency and insight into protection rationale, critical for operations, audits, and modifications. Summary: the IPF narrative is a foundational safety document that captures the full design and operational detail of each protective function. It bridges the gap between process safety intent and technical implementation, ensuring consistent, auditable, and reliable execution of safety instrumented functions. Detailed IPF narratives. Purpose and requirements. Detailed IPF narratives provide a structured, comprehensive description of each individual instrumented protective function IPF within a process unit. Their purpose is to clearly define how each IPF mitigates a specific hazard, including the detection logic, actuation path, and conditions for successful response. This level of documentation is essential to support safety integrity level SIL assessments, system configuration, FAT/SAT testing, and operational readiness. Every IPF must be treated as a standalone protection layer, even if implemented within a shared UZ block or safeguarding diagram, because each is designed to address a distinct hazard with its own logic, response-area, and performance requirements. Narrative structure for each IPF. Each IPF narrative contains 4 core components. 1. Objective. This section identifies the hazard the IPF is designed to prevent or mitigate. It includes design intent. What specific process risk is being addressed, e.g., overpressure, overheating, backflow, high liquid level. Consequences of failure. A realistic assessment of what would occur if the IPF failed to act, covering safety, environmental, asset damage, and reputational impacts. Justification. Why an instrumented function was selected over mechanical safeguards or other layers of protection. This forms the basis for risk reduction calculations and SEAL classification. So 2. Functional description. This describes how the IPF works from sensing to final action. It covers initiators, sensors or transmitters used to detect the hazard. Each initiator is identified by tag number and description. Grouping and voting logic, e.g. 101, 203, must be defined, including success criteria where multiple initiators are used to back each other up. Demand scenario defines the conditions under which the IPF is expected to activate. This helps determine how frequently the IPF will be called upon to operate, informing SEAL assessment. Final elements lists all actuated elements, valves, shutdown systems, trips that perform the protective action. Each is identified by tag number and service. The number and combination of final elements required to mitigate the hazard must be stated, e.g., at least one valve must close or all must close to isolate completely. Primary actions, those directly responsible for hazard mitigation. Secondary actions, actions that help recover the system or prevent secondary impacts, e.g., tripping upstream equipment, isolating related subsystems, but do not directly mitigate the core hazard. The narrative must describe all logic relationships between initiators and final elements and reference the appropriate cause and effect diagrams and PEFs. 3. Operational and implementation aspects. This section captures how the IPF is used, tested, reset, and integrated into plant operations. Modes of operation defines when the IPF is active, e.g. startup, normal, shutdown, abnormal. Some functions may be mode specific. Safe state definition states the process condition achieved once the IPF activates, e.g. depressurized, isolated, vented. Response time states the time allowed to bring the process to a safe state after detection. This includes stroking time of final elements and any delay logic. Process safety time is critical for verifying whether hardware and logic are fast enough. Manual reset override describes whether the IPF requires manual reset and whether bypass or maintenance override functions are available. Also indicates if overrides are time-limited or alarmed. Calculations. Any calculations embedded in the IPF, e.g., derived values, filtered signals, voting logic, ratio-based triggers must be described and justified. Failure modes details how the system is designed to respond to common failure scenarios, e.g., sensor fault, valve failure to close, logic solver loss. Includes defined responses and any diagnostic coverage. Maintenance considerations covers whether overrides are grouped, how routine testing is conducted, and what conditions must be met for safe testing without removing protection. This section ensures the IPF is not only well-designed, but also operable and maintainable within a live process environment. 4. Logic and sequence representation. If the IPF involves non-trivial logic or coordination, especially in furnace startup, batch control, or shutdown sequences, this section includes narrative logic flow, a written description of the step-by-step progression of the IPF logic. Structured pseudocode, where appropriate, simplified logic is expressed in structured English. Functional logic diagrams, FLD, and sequence function charts, SFC. These diagrams graphically depict the flow of logic and conditions between steps, aiding implementation and testing. Interface signals. Cross-system or inter-unit signals involved in the IPF are also detailed, including tag names, data types, and source-destination systems. Implementation timing. During the definition phase, functional intent, logic structure, and process safety time requirements must be established. During the implementation phase, full configuration details such as final device selection, diagnostic strategies, and exact timer settings are finalized and incorporated. Summary. Each IPF narrative represents a critical element of the overall process safety strategy. By clearly defining objectives, logic, implementation details, and operational behavior, these narratives enable consistent system configuration, facilitate SIL classification, support commissioning, and provide long-term value as part of the plant's safety lifecycle documentation.